We are now in Chapter 6. This is the last chapter that we're going to cover with a lot of sections, but last chapter we are going to now be talking about applying our integrals with vector fields. And we're going to learn some really important theorems that can be used to solve some integration problems. So in this section, section 6.1, I am just going to give you an introduction to vector fields. I just want to explain exactly what do I mean by a vector field and how can we start to visualize that. So a vector field is basically a collection of vectors. So vectors are assigned to every single point in the domain. You can have a two-dimensional vector field. That's what I'm saying in this first sentence right here. You can define your vector field in R2 in two-dimensional space. That's what I have shown on this screen. These are two-dimensional vectors. Or you could have a three-dimensional vector field in space with three-dimensional vectors. And so vector fields are great ways to describe forces or describe stream function, flow of motion. That's what I have in my pictures, two kind of pictures of vector fields. So vector fields are used frequently in science and physics applications. So the first thing I want to be able to do is I want to talk about how do we actually sketch a vector field? How do we visualize this vector field? So we've got the vector field F equals yi minus 2xj. And so the idea here is that a vector can be assigned to every single point in the plane using the definition in this equation. So the x component of that vector is always the y coordinate, and the y component of that vector is -2 times the x coordinate. And so I'm going to create a graph just by plotting a bunch of vectors. And so I started by just drawing my kind of two-dimensional coordinate system. And then I'm just going to pick points. That's what I kind of tried to indicate by these little dots. I'm just going to pick points, and I'm going to compute what is the vector at each of these points, and then I'll draw that. So for example, if we want to consider, I'll just do this row of points right here. So the point x is -2, I guess that would be up here, -2, 2, -2, 1, -2, 0, -2, -1, -2, -2. So that's my collection of points, and I'm going to go through and I'm just going to compute what is the vector with each one of those points. And to do that, I'm going to use the equation that they gave me. So the first component of my vector is always the y value. So at the point -2, 2, I get y component, or y coordinate is 2. So I'm going to get 2, and then I take -2 times x. So -2 times -2 is 4. And then I went through and I did that for the rest of these points. So I basically just took the x's and y's in this collection of points, and I plugged those into my vector equation to get a bunch of vectors. So I've got the vector 2, 4 at the point -2, 2, 1, 4 at the point -2, 1, etc. And then I'm going to go through and I'm going to try to plot each of these vectors at those points. And I did all of them. Let me slow down a little bit. So let me just show you the first one. So at the point -2, 2, so I'm at this point right here. I'm just going to draw a vector that goes over 2 and up 4. So there's my vector at the point, starting at the point to -2, 2. And then I'm just going to go through and do the same for each one of these. And so that's what I have drawn in these blue arrows. So I went through and I tried to draw each of these vectors that I computed in my list. And then I'm going to continue doing this for just a collection of points to create a visualization. So how about we do this next kind of column right here, this bunch of points. So we've got the point negative 1, 2, negative 1, 1, negative 1, 0, negative 1, negative 1, negative 1, negative 2. So those are all my points. I'll take those x's and y's and I'll plug them into that vector equation that was given. So into this vector equation right here. And then I'm going to go ahead and plot each of those vectors. So for example, I know this is getting a little bit messy. I tried to kind of modify the color slightly, but for example, at the point negative 1, 2, so this point right here, let me just show you what I did. I plotted the vector 2, 2, so I went over 2, up 2, so that's the vector 2, 2. And then at the point negative 1, 1, so right here, I plotted the vector over 1, up 2, and then I plotted this entire list of vectors. And again, I obtained these vectors by plugging in my x and my y into that vector function that I was given. All right, I did the same thing now for the points along the y-axis. Shifted the color slightly just for clarity of viewing. So plugged in the x and the y values into my vector function. Got a bunch of vectors, plotted those in purple. And then I'm going to do the same thing for my next column of points. I've got a bunch of x's and y's. I plug those into my vector function. Computed the vectors, plotted those vectors in red. And then let's do one more. Oh, actually, I'm going to pause. There was another question in this problem. It says, what is the vector associated with the point 1, 2? We actually computed that in this column, so let's just jot that down so we don't forget. So the vector associated at the point x equal 1, y equals 2 is this vector right here, 2, negative 2. All right, and then last set of points. Again, I just listed all my points, my x's and y's, plugged them into my vector function, got a bunch of vectors, plotted them in red. And so this is a nice visualization of this particular vector field. And so what I can see in this vector field is it does look like I see kind of a clockwise motion. That's what it looks like to me. So if you imagine that these were winds, it does look like you have some type of motion, clockwise motion there. It also looks like as you get further away from the origin, the vectors are getting longer, the magnitudes are getting bigger. And so that's what I notice about this vector field. Now, this image is getting a little bit messy. It's kind of hard to see. All these different arrows are overlapping each other. It does help that I use different colors. Another thing I could have done is I could have chosen points that were further apart. Maybe the vectors wouldn't have overlapped quite so much. Or another option, something that I frequently do to visualize vector fields, is sometimes I'll try plotting vectors of equal magnitude, of equal length. So now think about what that looks like. So in this particular case, the magnitude of my vectors can be found by taking the square root of my x component squared plus my y component squared. So magnitude of this vector field would be the square root of y squared plus 4x squared. And then I'm going to consider, where am I going to have vectors with a magnitude of 1? So I'm just going to set this magnitude, this square root y squared plus 4x squared equal to 1, square both sides, and I end up with the equation of an ellipse. 4x squared plus y squared equals 1 is an ellipse centered at the origin, and that's what I tried to graph on my axes. So that little ellipse I drew in red are places where the vectors have a magnitude of 1. And then I went ahead and I did the same thing, setting this magnitude here equal to 2. So square root y squared plus 4x squared equals 2. Squared both sides, and I got another ellipse, an ellipse with a It's a little bit larger. That's kind of the ellipse in the middle there. And then I set my magnitude equal to 3, squared both sides. 4x squared plus y squared equals 9 is yet another ellipse. That's kind of the third ellipse that I've drawn in my picture, all centered at the origin. So these are all places where my vectors have an equal magnitude. And so what I said earlier is true. As we go away from the origin, the magnitude of those vectors is getting larger. And so then what I can do is I can just pick a couple points and plot some vectors to see what it looks like. And so just for simplicity, I chose the points that were sitting on the axes. So I chose this point right here. What is that? X is 0, y is 3. So that would be the vector 3, 0. And that's exactly what I've graphed. And then I just went ahead, plotted some more. And I can see that same kind of rotational motion. Magnitudes are getting larger as we go out. So another way of visualizing that vector field. Again, I didn't show all my work here because I had computed these vectors in the previous slides. But to figure out exactly which way these vectors were pointing, I was just plugging points into that vector field equation. All right, second thing I want to talk about is a unit vector field. A unit vector field is one which has a magnitude of 1 everywhere. So every vector has a magnitude of 1. So is the vector field negative yx a unit vector field? To answer that question, I'm going to compute the magnitude of this vector field, square root of negative y squared plus x squared, or square root of y squared plus x squared. This does not have a magnitude of 1 everywhere, because if I plug in, say, the point 2, 2, the magnitude's definitely not 1. This would only be a unit vector field if I could get this expression to simplify all the way down to 1. That's definitely not happening here. So no, this is not a unit vector field. All right, so that is a little bit of vocabulary for us. The second vocabulary word I want to talk about is what we call a conservative vector field or a gradient field. So those words mean the same thing, a gradient field or a conservative vector field. And we're going to talk quite a bit about conservative vector fields in a future section, but for now, I just want to define the idea. So a gradient or conservative vector field is one such that our vector field is the gradient of some function. And just to remind you, the gradient vector, you take the derivative with respect to x, that's your x component, derivative with respect to y is your y component. So if your vector field is the gradient of a function, we call it a gradient field. That function f is referred to as our potential function. In this image, I have a picture of a gradient field or a conservative vector field. What you're looking at, the little arrows are my f's, my gradient field, and the black lines are actually level curves for that function f. And so my gradient vector, we learned earlier, is always orthogonal or perpendicular to these level curves, and that's exactly what we're seeing here. These gradient vectors are perpendicular to my level curves, and so we're looking at our gradient vector field. Again, we're going to talk more about this idea later on. For now, I really just want you to be able to compute a gradient vector field for a function. So for example, if I have the function f of xy equals 2x to the third y minus y squared, The gradient vector field is simply a vector field where the x component is our derivative with respect to x, and our y component is our derivative with respect to y. And so that's all I did to compute this vector field. Derivative with respect to x of my potential function is 6x squared y. Derivative with respect to y would be 2x to the third minus 2y. And that's my answer. That's all I have to do here. There's my gradient vector field. We can have gradient vector fields in three-dimensional space as well. You're simply going to be creating a three-dimensional vector. The x component is your derivative with respect to x. Y component is your derivative with respect to y. And then you're going to have a third component, which will be your derivative with respect to z. So we can have these gradient vector fields in more dimensions as well. So in this case, let's see, my function is x e to the negative z divided by y. So derivative with respect to x is e to the negative z divided by y. Derivative with respect to y would be a negative x e to the negative z over y squared, right? That's like a y to the negative 1, so negative y to the negative 2. And then finally, my derivative with respect to z is going to be, we're going to get an e to the negative z times negative 1. So that's negative x e to the negative z over y. And that is the vector field, or gradient vector field, or we could say conservative vector field for this potential function. So this is a relatively short section. Again, the point of this section is really just to give you an overview of vector fields. And then as we continue through this chapter, we're going to start doing some calculus with these vector fields. All right, that was my last example. Please let me know if anything is unclear.